Great. Thank you so much, everyone, for being here, and thank you for giving us this opportunity to share our work. This is joint work with John Kleinberg at Cornell and Matt Weinberg at Princeton University. And I'm going to talk about our work on modeling the dynamics of poverty, and we'll really use this as an opportunity to share several open questions that have come up that we think are going to be of significant interest to the economics and computation community. So as you all know, poverty is a huge problem everywhere on Earth, including here in the US. For instance, in Boston, which is where I'm based, it's estimated that something like 20% of the population lives in poverty or very close to poverty by some measures. And despite its prevalence, despite poverty's prevalence, we also know that it's very, very difficult to measure. So oftentimes what we do is we rely on simple measurements of poverty, like people's income or their wealth. And we use these simple metrics to make significant and consequential decisions about how families may or may not be getting much needed resources. But at the same time, there's also significant empirical and policy work over the past decades showing that these measurements, these simple measurements, are very insufficient. So the Poverty Tracker Study, which is based at the Columbia Population Research Center, has a series of reports that they've put out. This is just one example of many that I'll highlight, where they basically say that these official income-only measurements of poverty are actually quite optimistic, and they don't necessarily fully capture the full magnitude of disadvantage that families might be facing, right? And this is just really one study of many that make this point, and it's one that really has been a significant barrier in efficient allocation of resources across the US. So you might say, okay, if income is not really doing a very good job at measuring economic advantage, then what exactly are we missing? One missing dimension of economic disadvantage is income shocks. So these income shocks can constitute a delay in someone's income flow, like a delayed check or maybe losing your job, or it can be a sort of unexpected expense, like a huge medical expense, or even a small thing like a parking ticket. And there's a massive, massive body of work in sociology and economics that I won't get into that really shows the significant role that income shocks can play in starting or perpetuating cycles of economic disadvantage, and also shows that there's sort of a very common mechanism via which many different forms of disadvantage might be playing out. So I just have some kind of buzzwords here, essentially: household consumption dynamics, optimal taxation theory. I won't get into it because of time, but I do want to say that there's a massive body of work in the sociology and economics literature connected to the role of income shocks and the dynamics of income shocks. But what we're really interested in as people who study algorithms is whether we can actually come up with a simple model of welfare that incorporates not just people's income and wealth, but also their experiences with income shocks. And then also we want to see whether these models can help us inform allocation of the types of subsidies that we might see around in the US or elsewhere. So I'm going to show you a very stylized model that we were able to work with. It's based on the structure of Rohn processes. So we'll assume that we have N agents, which can represent families that a planner would like to assist. On the x-axis here, you have time. We'll assume that it runs continuously. And on the y-axis, you have the agent's reserve, which is sort of, let's say, how much they have at that given point that can help them buffer against any, being disadvantaged. So we'll assume that the initial reserve that an agent has is their wealth, which is denoted by the U sub I. So you can think of this as, say, how much they have in their savings and their assets combined at time 0. And the agents have a net income C sub I, I'll just call it income, which you can imagine as sort of how much they would earn on average per unit time minus how much they would kind of usually consume, right? So this is what they would have left over. So in the absence of shocks, then the agent's reserve is given by the simple expression that you see here. The agent's reserve, which is the R sub I at time t, is what their reserve was at time 0, which is their initial wealth, plus their income times T, right? So this is a simple expression, but we're in a setting where agents do experience income shocks. So what we'll do here is we'll model these shocks as a sort of sudden drop in the agent's reserve. Here you see 3 kind of drops that the agent has experienced. We'll assume that these shocks are arriving at randomly selected discrete points in time, so T1, T2, T3, and so on, and we'll denote the shocks corresponding to time T sub j as with S sub j. We'll assume that these shocks are arriving according to a Poisson process with arrival rate beta sub I. So note that this is indexed by the agent's this is denoted by the agent's index, so different agents can have different arrival rates. And we'll assume that these shocks, the magnitude of these shocks, or the magnitude of these drops that you see here, are drawn from some distribution f sub I. Again, different agents can have different distribution from which you're drawing their shock. So what happens when you experience a shock is basically I'll take the magnitude of that shock and I'll subtract it from your reserve at that point. So now your reserve here is what your reserve would have been if you hadn't experienced any shocks, minus the total magnitude of shocks that you've experienced up until that point, right? So this is an expression here that includes people's initial wealth and their income, as well as experiences with these income shocks that they are having. So our objective here, which is very deeply motivated actually by the sort of the sociological literature, especially on eviction, is to say that we assume that there is a sort of threshold, which we'll call the ruin threshold, where if you fall below this, then you now become significantly susceptible to experiencing eviction or poor health or job loss. So we're assuming basically that it's much more expensive and maybe undesirable to for agents to fall below this threshold. So we really want to do as much as we can to kind of keep them above this ruin threshold. And we're working in infinite horizon. So really what we're interested in is the agent's ruin probability. That is the probability that at some point in time that they might fall below this threshold that we've set at 0 here. So that's our object of interest, the ruin probability, which we denote by phi. And you can see that it's entirely determined by your income initial reserve, the arrival rate of the shocks, and the distribution from which we're drawing the shocks. And as a planner, we assume that we would like to, we want to minimize the sort of the experiences with shocks that people are having, and we want to do so by giving out income subsidies. So these income subsidies are this X sub I that's appended to the agent's income C sub I, so it changes the slope on the graph on the right-hand side that you can see here. And we also assume that the planner has a budget that they can give out, so the total amount of income subsidies that you're giving out at any point cannot exceed some budget fee. And the planner's objective for now will denote as the min sum objective, which says that you want to minimize the expected number of people that experience ruin, but we'll also consider a different objective that we'll mention later. So with all these ingredients in place, we're asking how can we optimally allocate these income subsidies subject to this budget constraint? And we also ask, do these solutions give us sort of any insight into the nature of welfare beyond what we may have been able to gather from, just looking at people's income or other sort of more simple metrics that we had before. So I'll show you quickly sort of a very simple, a special case that kind of gives you a flavor of the types of problems that we were solving. In this case, we imagine that the agents have 0 initial wealth. So they're starting exactly at the sort of the ruin threshold. And this is a well-motivated example. This is assuming that agents are sort of living paycheck to paycheck, for instance, right? And we also assume that that agents have positive drift, meaning that the expected change in reserve per unit time per time is positive. So their ruin probability is going to be strictly less than 1. And we also assume that the shock size distribution, the F sub I, is only given to us by the mean. So we only know the mu sub I, the mean of the shock size distribution. We don't really know anything else about it. We make a mild assumption. We say that this distribution has finite mean and variance. And under these assumptions, there's, thanks to the probabilists, there's a simple expression here that shows the that gives you the ruin probability, which is that on the numerator here, you have a sort of the expected magnitude of shocks that they experience, and on the denominator, you have the agent's net income, right? So this is a simple expression that we can rely on in order to make our optimal allocation of income subsidies. So our objective function, the min-sum objective, can now be rewritten as what you see on the second line using the expression from the previous slide. And our goal here is to minimize fee with respect to our income subsidy, but optimally spending our income subsidy. And so we'll take the partial derivative of this function with respect to the x sub I, and it gives us this expression that you see here. You can take the second derivative with respect to the x sub I, and it will show you that this phi is strictly convex. And so what this says is that a simple kind of greedy water filling algorithm that will give you the optimal solution, right? So what you want to do here is you want to order the agents in increasing order of these partial derivative that you see here. So agent 1 has sort of the most negative value, and agent 6 has the least negative value. And we'll proceed by first increasing the x sub 1, so the x sub I of agent 1, up until the point where their partial value matches that of agent 2. Then you increase agent 1 and agent 2's up until the point where they match agent 3 and 4, and you just keep going until maybe you've assisted all the families or you've run out of income subsidy, right? So this gives you the optimal solution, but perhaps maybe equally interestingly, what we have here is that you have a sort of priority index, right? So this says that not only can you find the optimal solution, but actually I'm going to tell you the order in which you should be targeting families to achieve this. So you might ask, well, you did all this stuff to get to this point, but maybe this ordering that you have from these priority indices is the exact same as what you would have achieved if you just order the agents by their income, right? How different can the priority index by our solution be from the ordering that just goes from the person who has the smallest net income to the person who has the largest? And as it turns out, actually, I can give you a very simple expression. We won't get into it in the interest of time, that shows that our optimal solution can be the exact reverse. It can give the exact reverse ordering as the ordering induced by the agent's income, right? So basically, if you're going by the agent's income, you might actually be targeting the person who's maybe the least receptive to your intervention here than what the optimal solution would say, right? So this shows a sort of significant difference that taking into account people's income subsidies can incur in our solution. And in fact, we show that there's a sort of significant gap between our optimal algorithm and any algorithm that only uses income. Again, I'll refer you to the paper if you want to take a look at the details. But these kinds of solutions actually, these kinds of counterintuitive results actually kind of kept appearing in our project. So I had mentioned to you about the min-sum objective, but you could have also looked at a min-max objective that just says, I want to minimize the maximum ruin probability that I see. Both of these seem like very reasonable objective functions. And in many special cases, including this one actually, then both of these solutions actually give you a sort of a priority index over the agents. But again, we find that actually in using the exact same example that I showed you earlier, actually, that the ordering of the agents can be the exact reverse, right? So you could be optimally solving for the min-sum objective versus the min-max objective, taking into account exactly the same parameters and exactly the same intervention, right? The income subsidy, and yet it can tell you that you should be targeting, an entirely disjoint set of agents if you're optimizing for min-sum versus min-max. And this surprising result again carries over actually even if you change the intervention. So if you fixed your min-sum objective, but instead of giving agents an income subsidy, you decided to give people an initial wealth subsidy, right? So just like a subsidy that changes the y-intercept rather than changing the slope from the graph that we see on the right-hand side. So under these two subsidies, again, you can actually have these fully reversed orderings of the agent's priority in the order in which you should be targeting them. So what these kind of tell us is that there's sort of these deeper societal implications to our results, right? The first result about the agent's income versus the ordering by the agent's income versus our ordering says that what information you're taking in about families can matter significantly. The second result says that the objective function that you're using here can matter significantly. And the last one says that the type of intervention that you're looking at can also matter significantly. And there's actually a broad discussion that we have in our paper, just sort of going through some of these discussion points that I highly encourage if you want to take a look. So now that I've kind of given you a flavor of the result that we have here, I want to kind of quickly go through the more general case. So how do you optimally allocate these income subsidies in this more general setting? So here we're going to assume that your income wealth can be any arbitrary values. They're positive. We assume they're positive. Your shocks can be drawn from any sort of general distribution. In fact, we don't even assume that this distribution has a compact representation. We'll just assume that it's sort of given to you in a black box fashion. And we also now drop this assumption about positive drift. So we say that actually your drift can be negative, meaning that your ruin probability can be 1. So in this setting, I could be giving you an income subsidy, and for a while, actually, your ruin probability can just stay 1 because your drift is becoming less and less negative, but it's still negative, so your ruin probability is 1. So in this setting, unsurprisingly, the objective function that we were working with is no longer convex, right? So we sort of have, we lose the ability to use the sort of greedy algorithm style solution here that gives us the optimal income subsidy, right? But even in the setting, actually, we find that we can give an FP task to optimize for the min sum objective. And given that we made very few assumptions on the problem, this was sort of the best that we could have hoped for, given the sort of the loss of the convexity and the few assumptions that we made on the problem. And I won't get into the proof idea here, but it's very similar to FP tasks for knapsack via dynamic programming. Highly recommend that you take a look if you're interested in the sort of the type of solution. Again, this is for the min sum setting for the income subsidy. So this is for our general setting that we have the solution. And I'll take the last minute to say that in some ways, a lot of what I think is exciting about this paper is the model. It's a very well motivated model. It's one that actually was a result of the very first MD4SG meeting that we had, where we read a bunch of sociological papers. And so we have this model, we have kind of our initial set of results here that you can take a look, but there's a lot of open directions that I think could be a significant interest to the EC community, both folks on the theory side of things and folks on the applied side of things. Just to highlight a couple, I'll say that, we assume that the shocks are independent. We also assume that the shocks are independent of income and your reserve, but in reality, we know that's not always the case, right? So incorporating dependencies would be one exciting direction. Also incorporating dependencies between agents by assuming there's a sort of underlying network would be another exciting direction. Also dynamic subsidies, right? We're now assuming that there's a sort of a static decision that you make in the beginning and that's it. But you could imagine that actually maybe the planner has the ability to change their subsidies over time. There's also sort of more empirical directions that you can take a look at. And I'll just say that I'm very excited to talk about any of these directions if folks want. I'll be around at the various breaks that we have, and also feel free to send an email if you would like to discuss any of this further. And thank you.